Hi everyone, my name is Alex. I'm here from a company called LightStep, and the marketing people asked me, before I tell you what LightStep is, a show of hands for anybody who's heard of us before. There better be a few. Okay, all right, that's good. Okay, great. Organizer doesn't count. Kyle, I wanted to see your hand up. I didn't see your hand up. I'm going to blow one slide here and tell you what we are. So LightStep we're a startup based in San Francisco in what's now sort of called the observability space. That wasn't a word that existed 3 years ago, but is all the rage these days. You can think of it, anybody who's familiar with a distributed tracing service, Dapper at Google or Zipkin or Jaeger or any of the other proprietary ones that maybe you've worked with. LightStep tries to provide distributed tracing services for companies that don't already have their own, which is sort of a two-part operation. We have to convince the company to instrument their code using a set of either open source or open standard instrumentation APIs, and then we accept all the data that those companies produce from their systems and provide the analysis and the storage and the visualization and so forth of that data. I hope I'm not overstating things to say that we sort of think of ourselves as a little bit of a leader in this field. Our CEO and one of our founders was Ben Siegelman, the guy who created Dapper at Google and has a sort of long history in this field. I got involved in this space that's now called observability while I was at Google. I was there for many years. I worked on Dapper for a little while there. I was one of the creators of the system called Monarch, Google's global monitoring system. I worked on a variety of storage systems there, one of which is the storage system that sits behind a lot of the Stack driver suite of products. So logging, tracing, monitoring, both internal and external. And finally, I worked for a little while on some stuff in GCP, virtualized storage products that Google sells. And I say all this just to sort of explain that I sort of feel like I have two hats in a gathering like this. One is as somebody who has spent many, many years building tools for people to help understand the performance of their own system, but also I have been somebody who has built systems whose performance I want to understand. And I think it's been a fascinating interplay between those two things, but I have kind of one foot in both camps. I want to spend a couple of slides here and look backwards before looking forwards, because I think it's maybe useful to understand how we got to where we are before we can understand where we ought to be going or what we could be doing better. So with a nod to Douglas Adams, maybe, I don't know if there are any fans in the room, but I'll characterize the era from maybe 2000 to 2010 as the era of survivability, of survival, I should say. So what did you measure as an application engineer in this time? Almost universally, at least in my experience, you measured the mean latency of your service over time. That was it. And it looked maybe something like this. You're a good engineer, so your service maybe looks like it needs to be resuscitated there. But great latency, very stable over time. That's wonderful. And why did you measure it? Mostly because you could, I think, is the answer. It's hard to remember how primitive things were in this decade. It was easy to measure mean latency, and you did it kind of because you could. And also intuitively, it sort of felt like mean latency was the answer to, well, is my service basically okay? That was the thing that people mostly cared about. And I mean, we still care about it now, but that's all they cared about back then. Is my service okay? Is the average latency okay? Yeah, okay, let's go home. I'm exaggerating a little bit, but only a little bit. I've heard people say what I just said. Fast forward 10 years, starting in about 2010, maybe a little bit earlier in some places, maybe a little bit later in some places. I know there's people who work for companies that weren't even founded in 2010 here, but it's sort of the ballpark of when I think things started to change a little bit. People started looking at their P99 latency over time. And I'm going to say P99 throughout this talk because I don't want to say more nines than that, but many people look at more nines. Interpret this as just a P99 as a placeholder for tail latency. This is what people started looking at. And you're a good engineer, so your P99 probably looked something like that. It's higher up, but you know, there it is. It looks okay. There were a few reasons, I think, why that shift happened. So one was obviously the development of the kind of modern cloud architecture that everybody is used to. You have a bunch of microservices, you've done a bunch of sharding so that you can scale, and when you do that, and this is well known, right, all of a sudden what used to be your tail latency now turns into your median latency, right, when you have a whole bunch of fan out for every single request. A second reason is that, and people have said this throughout the talks earlier today, nothing has changed in the last few hours. There's been an increased understanding of the marginal value of latency, right? If you can drive the latency of your website or your mobile app down just even a little bit, your revenue goes up. Still true from this morning. And finally, I think the third reason here is that there's been, maybe this has happened as a result of kind of the emerging DevOps or SRE culture that has sort of taken over the industry in the last 5 or 10 years. But people have moved a lot more towards characterizing and measuring and communicating the behavior of their system using SLOs and SLAs. And stating an SLO or an SLA like our P99 is less than such and such number of milliseconds, that feels like a guarantee to people. Even if it ends up not being a guarantee, it feels like you're making a good guarantee. And everybody likes guarantees. So I think those are some of the reasons why we got to where we are today. But this is the progress that we've made in 19 years. So, good work. Pat yourself on the back. It's progress, I think, but I think we can do a little bit better maybe. I get to make jokes like that because I was responsible for this at Google in large part. So I want to be clear that I'm making fun of myself here in large part. Sorry, those of you who are at Google. All right, so let's look at some actual latency distributions here. So these 6 different histograms here are actual latency distributions over, I don't know what the time window is here, an hour or something like that, from 6 of our actual customers. I know what I'm looking at here, and I still think that this stuff is sort of crazy all the time. You can't see the axes, but it's on a log-log scale. So the dynamic range on the x-axis, the latency range, is profound here. It's covering, well, I can't even read it either, but I think it's covering like 3 orders of magnitude on the x-axis there for a lot of those. So I have no idea what's going on here. These things, maybe the ones highlighted there, maybe those are cache effects. I don't know. They're so much faster than everything else going on in those 2 plots. They've got to be an error path or a cache effect or something like that. Several of these histograms show kind of a double humped pattern. I don't know, maybe it's a back off and retry thing, maybe it's 2 different classes of requests that these services are seeing. I don't know, but it's clearly something going on there that's different. The one that looks the most maybe textbook normal-ish is this one in the bottom left, maybe. That sort of linear-ish slope down into the right in log-log space corresponds to a power law distribution, which you might be happy to see in a textbook. But even there, you can see 1, 2, 3, I don't know, maybe 4 different humps and a funky thing going out on the right-hand side, so it's not nearly as simple as just a vanilla power law. It's not just us. This is a data set from MIT, a publicly available data set. What they did was they took 2 endpoints on the internet and they just sent pings back and forth. That was it, and measured the latency of those pings. And this is the histogram that they got out. The y-axis here is not a log scale anymore, but the x-axis still is a log scale. So it's, let me see here, I think it's a factor of like 500 in latency across the bottom there from the left to the right. So an enormous, enormous range in latency here. And you can count, I don't know, again, 1, 2, 3, 4, maybe 5 or 6 different modalities that you can see in this distribution. And I have no idea what they are, but they're clearly different, right? Just by glancing at this, you can see there's a lot of different things going on that are sort of hidden in this distribution. Before I go on to the next slide, you can avert your eyes if you need to. There's going to be one equation. I'm a mathematician by training, and I'm holding the microphone, so I get to show one equation here. So if this is something that I wish, this expression, I'll tell you what it means in a second, is something that I wish a lot more practitioners in our field had good intuition for. Almost nobody I talk to knows what this is. This is the expression for the sample, the variance of the sample quantile. Okay, so the idea is you have some distribution, and you take a sample from it, and you look at a quantile of interest, P99 or P95 or whatever it happens to be. And then you do that a whole bunch of times, and you're essentially getting a different measurement, a different estimate of the quantile for each sample that you've taken. Well, it's a random variable. You can ask, what's the variance of that random variable? This expression gives you the variance of that random variable. And you can see I'll explain what the different components here are. So the Q here is the quantile of interest. So this is going to be a number between 0 and 1, and you can see that it's symmetric around 0.5. So that intuitively makes sense. The P99 should behave basically the same as the P1, right? Everything is just flipped, so that makes sense intuitively. The n in the denominator is the size of the sample, so that's good. If you pick a much bigger sample from the distribution, your variance is going to go down. It goes down linearly. And this final term in the denominator is sort of the interesting one. This is the one I want you to sort of remember if you can. So this expression f, the capital F, is the cumulative distribution function, right? So it's saying, take the percentile of interest, the P99, whatever it is, go backwards, that's what F, capital F inverse is, go backwards to the value that that corresponds to. Lowercase f is the probability density function, right? So ask, okay, what's the density, the probability density near that value, and then square it. And that feeds in here. So intuitively what this is saying is that in areas of your distribution where there's not a lot of density, you're going to have a lot of variance in this sample quantile measurement, which intuitively makes sense, right? If you've got sort of a long range of values and not a lot of density there, and you're asking for a quantile measurement there, it's going to kind of naturally bounce around a lot. What I always have to remember is that there's a squared factor in there, which is crazy. You get a lot of bouncing around as soon as the region of the distribution that you're in starts to have very little density. You get a lot of bouncing around in your sample measurements. And I should say this is kind of particularly important for tail latency estimation because by its nature, estimates out at the tail of your distribution are going to be in a regime where there's not a lot of probability density, right? If there were, it wouldn't be out at the tail, right? All right, so what? So real systems are extremely multimodal. This is not news, but it's something that I think we need to keep reminding ourselves of over and over and over again. But quantile statistics, which are used universally to understand the performance of these systems, are really reductionist, right? You remember that plot of the mean versus the P99? All that changed was that the P99 was higher than the mean, and it was noisier, and that was sort of it. Both were I would say, were kind of equally useless for understanding the actual modalities going on in these systems, right? So these quantiles hide a whole bunch of distinct behaviors and behavior changes. I was showing you sort of snapshots in time, but you could imagine the same thing happening between a distribution measurement now and one tomorrow or next week. And I've sort of given away the lead here, right? But I think the conclusion here is that these percentile measurements are so reductionist as to be not useful at all for actually understanding system behavior. Maybe they're helpful a little bit for communicating SLOs, although I think there's problems there also, but they're really, really not useful, I should say, for understanding systems. All right. So what we can do? We can go home. That might be one answer. I don't think we should do that. They would fire us if we stayed home for too long. The next few slides I want to go through three things, a couple of which we have done or are doing at LightStep, and then one more which we haven't done much of, but is universal, and I think you guys could go back to your companies and apply at your companies. But I want to walk through three sort of specific things and ways that we try to think about this problem and ways we can take advantage of this problem. All right, so the first thing here is that we need to try to understand the distinct behaviors that are going on in these, that are reflected in the distributions, but which are hidden by quantile measurements. And there's kind of two steps here. So one, and some previous speakers have kind of alluded to this idea, but there's sort of two steps here. So one is to try to automatically, or really semi-automatically in most cases it turns out, you need a little bit of human input, try to identify different subpopulations of your global population that might have different behaviors. And then the second thing, once you've identified those subpopulations, is to try to figure out which of those have behavior that correlates with the SLI or the SLO that you're actually interested in, right? At the end of the day, the thing you care about is some business metric. Try to figure out which subpopulations correlate their behavior with that business metric of interest. So I can give you an example here. So this is a picture from one page in our product. So let me explain what we're looking at here. So on the top, is a latency histogram, and again, we're back to the log scale here. I apologize that we keep changing axes, but everybody has a different opinion about what should be used. The top there is a latency distribution from a service, I think again sort of measured over a period of 1 hour. And this data is derived from distributed traces. So what we've done is we've taken a whole bunch of traces that came in from a customer and plotted, formed the histogram there of their latency. Each of those traces has a bunch of rich information attached to it. What are the names of the spans involved? What were the operations involved? What are tags on the spans? People love to tag their spans with, a user ID or the geography that of the host name of the server that served the span, things like this. So there's a whole rich set of tags that tend to be attached to these traces. So what we've done is we've taken each one of those tags and coded it as a 0 or 1 binary variable, and then looked at the correlation between that variable and the latency of the whole distribution. I should say the latency of the traces on which that tag appears. And we have those on the bottom right, where we've surfaced the tags that have the highest correlation or anti-correlation, we care about the absolute value, with the overall latency of the distribution. And that tag there that's highlighted on the bottom right, you guys can probably read it better than I can, service API, whatever it is, which has a 0.64 correlation coefficient. The black bars in the top correspond to the traces that have that tag on them. So you can see it's a pretty decent correlation with the overall, between that tag and the latency of traces with that tag. I hope that's not for anybody in here. And we've found that this is a profoundly useful tool for very, very quickly identifying what's happening out at either end of the distribution. Let's see. Well, there were arrows that I was supposed to click on earlier to show you guys what was going on. Here's a slight variation on that. So instead of having the system sort of volunteer the tags that have the highest correlation with the latency, you can instead sort of flip it. So in the top section now, what I've done is dragged over a section of the latency distribution. So I've picked one of those humps that maybe I think is interesting and highlighted it. And the correlation that I'm now being shown in the bottom right is the tags that most highly correlate with the binary property of being in that section that I've dragged. Okay, so the correlation is a little bit less good here. There's some of these database operations select traces that are inside, and there's some that are outside. But as an exploratory tool, I think this kind of thing is extremely useful for very, very quickly getting a sense of what's going on at different modalities, at different humps in your distribution. And I should say our customers are quite happy with this sort of thing. Many of them have not used sophisticated tools at all to measure their systems, and they see something like this and are very happy. And it's something that you guys could go back. You could give this to an intern and come back in 2 weeks, and an intern could build this for you. It's really very straightforward, and I would encourage you to do so. There we go. I got to remember the arrows. I apologize about that. Okay, so number 2, what else can we do? We can try to use real statistics to understand if behavior has changed. So here's what I mean by that. Here's a fun game you can play. Or at least a game. I don't know how fun it is. Get some friends on a boring Saturday night, and here's the game. One person presents two samples, and those samples can either be drawn from the same underlying distribution or from 2 different underlying distributions. And everybody else has to guess which it is. Did the samples come from the same distribution or 2 different distributions? So here, I don't know. I have 2 here. You tell me if they come from the same thing. I've made it a little bit harder for you by the x-axis. The bounds on the x-axis are not quite the same on these 2 things, which makes it harder. I don't know, maybe they're sort of the same. I'll give you a little bit more information here, which is that the means are almost identical here between these 2 samples. The P99s are almost identical, but the P99.9s are very, very different. So I don't know about you, but if I, for example, released a new version of my software and the P39s went up by 20%, I would say, oh crap, that's not good, let's roll back right away, right? Turns out these are drawn from the same distribution. Okay, there is nothing different about these except they happen to be 2 different samples. All we're seeing here is that variance expression that I showed a few slides back. That's the only thing that's happening with the P99.9 here. You can play the game the other way, so this is much harder to do the other way. I mean, that wasn't easy, but this is even much harder. But this is essentially what we're doing. If you do a release and you go look at your dashboard and you look at a squiggly line, this is the game that you're playing right here. So I give you 2 samples, and all I'm going to tell you is that the difference in P99 is less than 5%, and the difference in the P99.9 is less than 1%. That looks great. If I did a deployment and those were the changes in my tail latencies, I'd say, great, let's push it to all of production. Go for it. These 2 distributions are totally different, and you can see it up here. This is on a log scale vertically again. The right-hand side has a cache in there, right? There's a whole, I think it's 40 or 50% of the requests are hitting the cache there on the right-hand side. The left-hand side has no cache. It's a huge behavioral change that is completely hidden by the reductionist P99 tail latency measurements. So the message here maybe is that you're really bad at distinguishing different distributions, or whether 2 samples are drawn from different distributions. And even if you somehow have a good innate sense for that, your coworkers don't. All right? And the ops person who's responding to a page at 2 in the morning really has no idea how to compare these things. You got to let a machine do it. So luckily, the academic statistics community has spent many years studying this question, exactly this question of were these two samples drawn from the same distribution or not? I've listed, this is sort of a fun, you can get lost on Wikipedia going through these things. I think the particular test that you use for comparing two samples is completely uninteresting. I think the fact that you use any of them is the important thing. Pick your favorite and use that to decide when something has or hasn't changed about, in particular, the latency of your service. Here's sort of a drawing. This is the Kolmogorov-Smirnov statistic over here on the right. You just draw the CDFs of your two samples and you look for the maximum vertical difference between the two, and then you plug it into a table, and Kolmogorov-Smirnov tells you if something has significantly changed or not. This is much better than using your intuition. So we have started baking this kind of thing into our product. This again is something you could go home and you could do. You know, give it to an intern and give them a month and they could probably do this. We've started building some of these ideas into our product. So here's a sort of screenshot of a feature that we have coming up where one of our customers does a release of a new deployment, a new piece of code, a new configuration, what have you, and we look before and after that release event or configuration change and identify the services or the methods that have the most significant latency or rate changes or error changes. And we've presented these as percentage changes because people don't want to see something like your Kolmogorov-Smirnov statistic is 1.8. They don't know what that means, understandably. So we've sort of normalized everything to percentages, but what we're doing behind the scenes is using these statistical tests to surface things that we really think have changed and are not just a result of noise. People seem to like this. All right, so number 3 here. What is the last thing we can do? So here's a picture that's essentially taken from the Dapper paper. So this is like state of the art 2005 or something, whenever that paper came out. This is how almost all distributed tracing systems work today. You've got a whole bunch of applications running. You've got an instrumentation library, a tracelib linked into each of those apps that's doing some logic and instrumentation. It's sending traces or parts of traces over to some local collector that's then maybe doing some work and finally sending some of those off, typically over a long-haul link to some global storage system. And there's almost always 2 different coin flips in a system like this. So one coin flip gets made, one sampling decision gets made in the app, and then another one gets made in the trace collector. There's a couple of motivations for these coin flips. So the one that happens in the app has 2 purposes. To protect the application, you don't want to swamp your app and burn a whole bunch of CPU cycles doing instrumentation. And you also want to protect the trace collector. You don't want to send too much data from the app to the trace collector, it will melt down. Typical sampling rates I've listed there. Dapper was published with a 1 in 1024 rate. I know that rate went up over time. I've heard from people at other large companies that this is sort of the right range of sampling probability that people tend to use. There's another coin flip in the trace collector, and the purpose here is a sort of similar thematically, but different in the details. So one is to protect the storage service, and one is to protect the WAN. You don't want to send an enormous number of bytes across the long haul link if you don't have to. And the sampling rates here tend to be much lower. So the Dapper paper suggested values between, well, 0.1 and 1, so between 10% and no sampling at all. And again, I've sort of heard anecdotally that this is kind of a similar level of sampling that a lot of people do. So this is totally wrong. We know a lot more than we did in 2005. These 2 reasons on the left for doing the coin flip in the application turned out to be not nearly as significant as people thought, I think. At least we can say that with the benefit of hindsight. So protecting the application turns out to not be as big a deal. You don't need nearly as aggressive a sampling rate to protect the application. Even web search, I know at Google, you could drive the sampling rate up to 1 in 16, and they were unable to notice a CPU or latency impact from a 1 in 16 sampling rate, even though they have, I would say, fairly sophisticated tools for understanding their latency and CPU consumption. It became almost invisible at 1 in 16 sampling. Protecting the trace collector, I think, also is something that is no longer necessary or is not as necessary. Collectively, the industry knows a lot more than it did 15 years ago about building really high-performance data ingestion services is one thing that happened. A second thing that happened is that the networks are a lot better, and in particular, the network software is a lot better. We're kind of on the cusp of an RDMA revolution. I think it will, in the 2020s, the next 10 years, it will be even easier to offload lots and lots of data for almost no CPU off of a machine to a remote collector. So when you do that, you can play with these sampling exponents. So you can drive the sampling rate way down, or rather, sample more, I should say, keep a lot more data in the app. And correspondingly, in the trace collector, you still have this problem of not wanting to pound the wide area network or pound the storage service. You got to make the exponents kind of line up. But you can move a lot of the sampling from the app to the trace collector. And what that lets you do is buffer data in the trace collector and do much, much, much more sophisticated things about how you sample. And I won't go into a bunch of details, but one feature that we tend to look at in our sampling, so LightStep's architecture looks almost exactly like this, is that when we do sampling in the trace collector, we try very, very hard to sample traces across the whole range, across the whole latency range. So in other words, we're sampling approximately the same number of tail exemplars as we are P50 exemplars, which is not true for anybody doing uniform sampling. You're doing uniform sampling, you're getting many, many more from kind of the body of the distribution than you are from the tail. If you do sampling like this slightly more intelligently, you can get a lot more interesting stuff kept from out in the tail. You can keep traces that have an interesting error condition, for example, with a much higher probability than you could with any kind of uniform sampling, or even, I should say, with any kind of semi-smart sampling that you might do in the app. When you're doing all that sampling in the app, you're throwing away so much that you have no chance to recover downstream. So this is kind of an architecture that I would sort of argue that if you all are building your next generation systems, think about moving some of the sampling logic off of the host and into a location where you can do a much smarter, much better job of capturing more interesting behaviors. All right, so what else can we do? This is sort of a grab bag of things. I'm not going to talk about these very much. Anomaly detection, root cause analysis, lots of people talk about those. I'm not going to talk about those. I think we can do them with a lot of this data, but I'm not going to talk about them. The variational analysis of cohorts of traces. So for example, take a pile of traces and look at the critical path, the critical latency path through all those traces, and now ask the question, okay, which span, which step in this trace should I shrink in order to have the greatest positive effect on the overall latency of the trace? Right? Where's kind of the lowest hanging fruit in this trace or in this collection of traces to improve? And that maybe sounds like sort of a contrived discussion, but a contrived question. But I can't tell you how many times I've done this myself or been on teams with people who have spent, I'm going to go spend a month. I'm going to improve the latency of that service over there. It's going to be great. It's going to improve web search performance. It's going to improve ad serving latency, whatever system they were working on. They go off for a month. They do this great work. They shrink the latency of some piece by 50%. They did a great job, and it has almost no visible effect on the overall latency of the system that they were a part of. This happens over and over and over again. And I think that the development of good tooling around helping us understand where we can get kind of the biggest bang for our buck or our time would go a long way towards improving that kind of workflow. Identifying hidden bottlenecks, I also won't say very much, except that everybody's sort of aware that when your system starts to hit, 70, 80 in that area, percent saturation, right? When your offered load becomes 70 or 80% of your total capacity, latency starts doing one of these elbow curves upwards, right? This is sort of well known. There's a lot of bottlenecks in distributed systems. A lot of them you're not aware of. Every mutex acts like a queue. There's a lot of explicit queues. There's a lot of thread pools that have bounded concurrency. I think it would be very possible to take large bodies of traces and look to see where they might exhibit the behavior of these sort of hidden queues. I think you can look at those distributions and say, this thing is starting to exhibit the characteristic behavior of what a queue looks like or what a lock looks like, and surface that for application developers and say, hey, even though you're not aware of it, it's not at the top level of your service. If you increase offered load by just 5% more or 10% more, you're going to start bottlenecking on this mutex that's in here, or this thread pool that's in here, or this queue that's in here. I think a lot of that data is stuff that we can get out of the trace data by synthesizing distributions and looking at the characteristic behavior of those distributions. So anyways, there's a whole long list of these things. I had to sort of trim this list a little bit to not go overboard, but there's a lot of interesting things to do in this space, I think. So anyways, so just to summarize here, I think we're maybe sort of on the cusp. The next 10 years, I'm optimistic. This is one of the reasons I continue working in this space, is that I think we're sort of on the cusp of of being able to take significant steps forward in our understanding of systems. And these are sort of three things that I've highlighted that we're looking at, but I do want to emphasize that there's a long list of things that we can do by looking at aggregates, by looking at distributions, that historically we as an industry have not done a very good job. We've kind of ignored that data and been willing to look at just very reductionist statistics that I think in retrospect have not helped our cause a whole lot. So let's do better the next 10 years. Thank you, that's all.
Hey, this is Ritesh from LinkedIn. Great talk. Just like you, I love histograms. I've been trying to use histograms for a long time. The problem is, as you saw in the whole session today, a lot of people talking about regression, catching regressions. And the way we catch regressions is looking at time series data. You plot time series data, see when things get worse, and compare before and after, right? So, is there a nice way to do time series for histogram data?
I think so, but
can you tell me about it?
So one problem I think here is the tooling, right? So if you look at like Prometheus or any of the other major open source, I mean, I know that very few people in this room are actually using open source time series systems, but maybe yours looks similar to those. Very few of them, almost none of them, have native built-in support for histograms. So I think that's sort of step one. When we built Monarch at Google, that was one of two reasons that we got the go-ahead to build it, is that we were willing in 2009 to build in histograms from day one. And I think that's one of the only decisions about that product that I don't regret. So anyways, but to answer your question, I think if you have a system for which histograms are first-class citizen, and you can ask your system to do arithmetic on histograms, it doesn't actually become very difficult to do the kinds of things I'm describing. Look at a 10-minute bucket here, look at a 10-minute bucket from after the change, and then do one of the statistical tests to ask if those are the same or different, rather than looking at a squiggly line, is what I would recommend. But
yeah, so you're right. If I'm comparing 2 points in a time, then I can compare histograms.
Yeah. I should say also, a lot of what I'm saying is not, I care about production systems and observing production systems. A lot of the things that interest people in this room are before you hit production, which I think is super valuable. But I will acknowledge that there's other techniques maybe that work better in a lab than the things I'm describing for looking at production. Yeah.
I'm Madhu from Facebook. So the architecture you described, do you see that working even for mobile phone-based apps, or that was mostly about how you measure things from the server? Because your first connection was a LAN over there.
Yeah, so my experience is entirely within the data center, so I wouldn't want to speculate. Somebody who's an expert on mobile would have to say more things, but yeah, sorry.
Hi, Anand from Apple. I can give both a question and an answer. For the question about mobile space, we have used very similar metrics, used the similar set of techniques to study the distribution of battery lives of devices in the field, and the same methods were very much applicable. Related to that, one of the problems we had was that in an organization, people usually find it easier to consume simpler metrics, and I was quite interested in how you normalize the results of something like the Kolmogorov-Smirnov test to make it consumable.
Badly is the answer. Whatever comes to mind first is probably as good as what we did. Yeah, I don't have any great answers for that. We kind of smeared stuff out to be on a 0 to 100 scale, just so it would look nice in the UI, but I don't think we have a lot of experience engaging with customers about what resonates best with them yet.
Hi, this is Samir from Google. I think, so my first question is, the statistical tests that you mentioned are fairly generic, they're distribution dependent. So one question is that, have you looked at any sort of parametric work or actually modeling these distributions so that your tests become more powerful? Or is there specific experience you have with some tests working better. And the other is that I know you actually talked about modifying the samples that you keep in the initial collector, but the flip side of it is more interesting, where the logging itself might have sampling bias. And have you built anything in your system which tries and suss out, no, you're actually just sampling wrong. This is garbage in, garbage out. So two-part question.
Yeah, so the first part is, for the first part, I guess there's things I could say about the statistical test. So yes, we have looked at some parametric stuff. It's not in any of our products, but we've sort of played around with it a little bit. As for the statistical tests themselves, I have favorites, but I think, which I won't tell you because I'm really serious that I think the most important thing is that you use any one of them and not which one you use. So I could tell you, but I don't think it actually matters. So this is the first part. The second part is, no, we haven't done, I'm not aware of anybody anywhere having done work to detect sampling bias coming out of the application. But I am aware of work in the instrumentation libraries to intentionally introduce bias. So what I mean something maybe pretty specific by that. There's two kinds of biases you could have. You could have statistical bias, which is sort of bad in some sense, right? You're doing some sampling and maybe you forget the weight or the probability that you sampled with. You lost it or you threw it away or you got it wrong or whatever. When you get way downstream, if you've got the wrong probability or no probability, you don't know how to reconstruct accurate statistics from that. That's totally bad. Don't do that, right? But there's another kind of bias, which is that I think should encourage, which is we should absolutely be biasing towards sampling things that seem novel or interesting, right? There's no reason to sample a whole bunch of traces that look basically the same that land near the P50, right? Don't waste your sampling budget on those. Intentionally bias towards the tail or towards errors or towards novel tags or whatever it happens to be. So we have done work towards intentionally introducing that kind of bias, yeah. I'm not aware of anybody else who has done that, but I think it's something cool that collectively in the industry should start moving towards.
A related question to the statistic tests. You said you have favorites, and is that how you choose which one to use? Because there is long list, and so question one might be, is there more things that you look at when you choose which one to use? And if, for example, you happen to choose two or more and they don't agree in terms of the results, what do you do?
Yeah, so the pragmatically, we made a choice that ended up being one that we thought we could more sensibly translate into a 0 to 100% scale. That was the pragmatic product reason for the couple that we ended up choosing. What happens when they disagree? We sort of throw our hands up and do our best. Yeah.
Your last comment about sampling, doing the tail base, the sampling, and the slide when you were suggesting to move the sampling from the logging side to the service sounds a little bit controversial, almost like you're sending the competitors to the wrong path. The question is, why not ship the distribution at the logging side?
So I'm very much not misleading. You can go, you can purchase our product and see that we do it that way. I would actually, anybody who wants to purchase our product, or if you want to purchase our company, you should talk. I shouldn't actually. I made that joke in a dry run of the test, and they told me not to make that joke. So now don't tell anyone. I'm not an officer of the company. I cannot sell you the company. So we do actually do it that way, and we're sort of all in on believing that that's the right way to do it. Can you ship the distribution back to the logging site? Yeah, I think you probably could. I think there has been not nearly enough exploration, or at least I'm not aware of it, I should say, around methods, instrumentation libraries that are able to get parameters injected into them kind of in real time. A lot of the instrumentation libraries that I'm aware of, you configure them at startup and that's it, and you go. And I think that I don't know if anybody's familiar with dtrace, this technology this kernel tracing technology that came out of Solaris and was built by by Brendan Gregg, who I think was up on the screen earlier. I think that we should build dtrace for distributed systems. That would be awesome. But the appeal there, right, is that you have these hooks and you can inject new logic into the hooks. Yeah, so we don't do it. I don't know anybody who does. I think we should.
Thank you.